acetylene will combine with the arsenic chloride, and it will lead to the formation of a gas which is called as lewisite gas. Very, very poisonous. In fact, much more poisonous than what Hitler produced, mustard gas. Remember, sometime back in the last chapter, we saw mustard gas formation. This is 4 times more poisonous than the mustard gas. Fortunately, Hitler was not there today. Otherwise, in his concentration camps, this will be running. Now, people have made this poisonous fellow, but they have also got its antidote. So in case if any chemical warfare begins anywhere, people have antidote ready, which is called as BAL, British Anti-Leucite. In case of nucleophilic addition, it's not easy. Why? For nucleophilic addition, you need to produce nucleophile which has excess electron. Yes or no? For that, you need to have a heavy metal cation with you. Why? These heavy metal cation will be able to produce nucleophiles, which will participate in the reaction. What are those heavy metal nucleophiles? Either mercury cation or lead or barium. These are considered to be heavy ones. Correct? If you use these cations, they will usually attract the pi electrons of the alkynes. Hence, they will decrease the electron density over the triple bond. Yes. Once the electron density decreases, who will attack? Obviously, the one who has excess electron, nucleophile, will attack. Yes. Unless until that happens, will ever the nucleophile attack here? Think about it. Triple bond means all the more heavy electron. Always electrophile will attack. Yes or no? But we are arranging a situation here with the help of some heavy metal cations. Yes. Like Hg2 plus or Pb2 plus or Ba2 plus. So that the electron density decreases. Yes. Because they attract the pi electrons. As soon as you bring an Hg2 plus here, what will it do? It will attach with them, thereby breaking one of the bonds. Are you getting my point? Yes. This is how they reduce, by they themselves participating. Understood? So when they do that, we will see that in the mechanism, don't worry. When they do that, after that it becomes easy for a nucleophile to donate their electron. Otherwise, previously already heavy electron density. Okay, so what do we use for this? We use dilute H2SO4 for this type of process. Since we are adding hydrogen, so nucleophilic addition is going to happen here this time. Correct? We are adding water, nucleophilic hydration is going to happen here. For that, what are we using? Dilute H2SO4 in the presence of mercuric cation. So, what will it form? It will form HgSO4, which is 1%, 40% sulfuric acid. Bring that. In this reaction, water will get added. First, unstable enol, unstable formation, intermediate will form. For this to get stabilized, what will happen? Oxygen will give its lone pair to form a double bond, and this will go here, become minus charge, and then later on plus H plus will come and attach here. So you will have aldehyde formation. Good. Here there are not sufficient number of carbons to form keto form. Yes or no? If there were 3 carbons, then keto form would have formed. Make sense? Is that clear? In place of this hydrogen, if there was an alkyl group, then we'll call a keto form. Otherwise, enol form changes, but this time it forms aldehyde. Good? Good. Here there are 3 carbons, so you will have keto. This is enol, this is keto. Yes, Risha.
Sir, like they're saying that enol is unstable. But I
Yes.
feel that oxygen will have lone pair, so double bond, single bond, and lone pair will be in conjugation. Resonance might take place.
That happens if you have those lone pairs on the carbon. If there's a carbon chain like this, where there's a double bond and here there is, negative charge, that means some excess electron is present, then they are in conjugation. We don't count that on oxygen.
Yes,
Correct?
yes.
Even though a kind of resonance is happening, but it is not a similar carbon atom. So even though these are pi electrons, that means p orbital electrons, but they are not moving from carbon to carbon. They are moving from carbon to oxygen or oxygen to carbon. which are not of comparable sizes. You're getting my point?
Yes,
That's
sir.
why they're not that stable. Understood? Good. But well thought. Okay. A structure in which hydroxy group is attached to the double bond carbon is called the enol one. Correct? That is what is forming here. Anyways, now this reaction is, why is it famous? This reaction is usually famous because of the formation of aldehyde and ketones. I hope you understand. Yes. So from this logic, can you tell me in which next chapter you will see them? Obviously, aldehydes and ketones, carbonyl compounds chapter. Yes or no? You will find them. We can make them in the preparation of aldehydes and ketones. We can do that with the help of nucleophilic addition of water, hydration reaction, using mercuric sulfate along with sulfuric acid. Good? Fine. Mechanism, let's see it quickly. As I told you, Hg plus will come, it will connect, then it connects on both sides, correct? Later on, water jumps on the other side, then H plus leaves to take care of the positive charge on oxygen. Yes? Am I going too fast in explaining this? Because we have seen this type of mechanism already. Yes? H plus leaves, this positive charge is taken care by that, OH remains. Once again, Hg plus will come. Once again, it will get connected. The whole procedure happens here. You can even go to single bond also. Correct? That also can be done. But here itself, when enol formation happens, this is not that stable. So then what will happen? Again, same thing. Keto formation. Correct? This breaks. And this will become CH3. You will have C double bond O keto formation, which is more stable. Nice. Understood? Good. One example right here in front of you. Good. Now, another nucleophilic addition, nitriles or cyanides. These fellows also most of the time leads to nucleophilic addition only. Why? Why do they lead to nucleophilic addition? Because they are the nucleophiles. They have excess electron, Cn minus. Yes or no? They have excess electron. So they are the nucleophiles. Whenever they attack at any electron deficient site, they will attack. But if you only react HCN with ethyne, they are not going to. You have to use some heavy metal. Is that clear? You have to use some heavy metal. This time, whom are we using? Barium cyanide. Why cyanide only? So that Cn minus concentration increases, at the same time Ba2 plus does his own magic. Nice or not? Ba2 plus has to do his own magic of connecting in the mechanism. Exact same mechanism will happen. As you saw here, that how Hg2 plus was connecting. Correct? Yes. Snatching electrons, then connecting with both the carbons. Exact same thing Ba2 plus this time will be doing. Good. Another important thing, this fellow, correct? This, if you have, let's say, 3 carbon chain, this is vinyl cyanide, let's say. If with this Cn, once it is connected, this fellow is called as vinyl cyanide or vinyl nitrile, whatever you call it, correct? So this vinyl cyanide has a tendency to polymerize. Why? Addition polymer. Via what? Addition polymerization will happen. Because double bond, na? Anywhere double bond means addition polymerization will happen. This is the polymer. So vinyl cyanide can lead to, or vinyl nitrile can lead to formation of one type of polymer which is called as Orlon. It can also lead to the formation of Buna in rubber also. Yes, these are all polymers in which vinyl cyanide can be used, and in polymer industries it is very famous. So nucleophilic addition first has to happen, then you have the monomer ready, which can lead to the formation of this polymer. Nice. Acetic acid addition, that is also very much possible. Acetic acid formation addition will lead to acetate. Yes, so you have this ethyne or acetylene with you. This is your exact same thing. This time, who is your nucleophile? Again, can you carry out this reaction without heavy metal? No. So Hg2 plus is used. Ag2 plus will reduce the electron density here. At the end, what will happen? At the end, what will happen? This is given to connect with oxygen. Yes. And this side, hydrogen leaves and connects here. Good. This becomes double bond CH2, O is connected here. Ethylidene acetate. Is this clear? Yes. Ethylidene acetate. Same way, let's say if you have vinyl acetate here with you, C double bond O, this side, vinyl fellow. If you have vinyl acetate with you and that is the monomer, correct? This double bond will break. This whole thing is like an attachment. This whole thing, the acetate fellow. This is acetate. I hope you understand. This is acetate. Good. And it is connected to this vinyl group. That's how vinyl acetate. Understood? Again, addition polymerization. Good. Yes. Supply some water. Hydrolysis will happen. Hydrolysis will cause this fellow to leave. H plus will come and join in that place. Sorry. Acetate alone to leave. H plus, O minus. H plus will connect here. Not here. Good. After hydrolysis, you will have alcohol here. Polyvinyl alcohol. From polyvinyl acetate, you obtain polyvinyl alcohol. Where is this polyvinyl acetate used? It is used in Fevicol. It is found in Fevicols, your Fevi sticks and all that. Correct? It is found there. It is an adhesive compound. Polyvinyl acetate. Nice. Good. Okay. Ethylidene acetates. Let's move down. What is time? Do we have time? Yeah, some more minutes. So when ethylidene acetate is heated, it gives acetaldehyde and acetic anhydride. If this fellow is ethylidene acetate, yes, two acetate groups are connected here. Can you see? Two acetate groups. Yes, in this ethylidene. Ethylidene because two ones are connected. And then when you heat them together, this CH3C double bond O will connect with another one. So basically this will attack on the other one and it will get connected, causing one more oxygen to come in the middle and this one of the fellows to leave. So one side breaks totally and goes away, which will form this CH3CHO. Other two sides gets connected, forming anhydride, acetic anhydride. Exact same procedure as above. Just because the structure is big, this is what happens. Good? Are we good? Okay. Addition of alcohols. Again, this time some or other heavy metal has to be there. See, it's like this. You're adding water. That is hydration. What did we use there for hydration? Ag2 plus was used. Yes or no? Either Ag2 plus or Ba2 plus was used. Here we did hydration. Let me go back and show you. Nucleophilic addition of water. Yes or no? We did hydration here. HOH is being added. We used what? HgSO4. At least 1%. Good. Now in place of HOH, you are adding what? ROH. That is alcohol. Anything different? You tell me. Anything different will happen? No. What are we using? Once again, this time mercuric oxide we are using along with BF3. Why are we using BF3? Electron deficient fellow. So what will this fellow will do? He will tend to give his electron to the electron deficient fellow, becoming himself electron deficient. Correct? Rest of the work will be done by mercury, and then oxygen will behave as a nucleophile and give his electron there and get connected. Nice. OCH3. Understood? OCH3 gets connected. This is what you get. And if you substitute, provide more of methanol, you will have acetal formation. Please see here, this is called acetal. OCH3 on the same carbon, correct? If there are only two carbons, but if there are three carbons, three or more than three carbons, then you will have ketal formation. This is called as ketal. These two terms are very important. Has come in exam in the past. Yes, acetylene will always form acetal. This is acetylene or ethine. Yes, this will form methylal or acetal, and anything more than two carbons, that means 3 carbon or more, will form ketal. Nice. Yeah. Only difference of this is there. Methyl group. Good. Fine. Same way, addition of arsenic chloride, this time in the presence of aluminium chloride or mercury chloride is more preferred, correct? Acetylene will combine with the arsenic chloride and it will lead to the formation of a gas which is called as lewisite gas. Very, very poisonous. In fact, much more poisonous than what Hitler produced, mustard gas. Remember, sometime back in the last chapter we saw mustard gas formation? This is 4 times more poisonous than the mustard gas. Yes? Fortunately, Hitler was not there today. Otherwise, in his concentration camps, this will be running. Oh my god. Yes, so ethyne combines with ACl3 forming 2-chlorovinyl dichloroarsine, because this is called as arsine, connected to arsenic, na? It becomes arsine. Yes, 2-chlorovinyl, and the second carbon, it is chlorovinyl, and then dichloroarsenic it is connected to, so arsine. In short, lewisite gas. Action of lewisite may be checked by its antidote. Now, people have made this poisonous fellow, but they have also got its antidote. So, in case if any chemical warfare begins anywhere, people have antidote ready, which is called as BAL, British anti-lewisite. They have made it actually, British fellows. So this, how is it formed? This combines with the lewisite to form basically a cyclic non-toxic compound. Correct? Anywhere, remember another important thing to learn from this name. Anywhere, if you have two SH fellows coming, yes, two SH fellows coming, or anywhere, even SH, anywhere SH is coming and OH is coming, there are two functional groups here. Yes or no? One is thioalcohol, another one is alcohol. Ol, thiol. There are two functional groups coming. Which one should be given higher priority? Obviously, alcohol. Yes, higher priority. Now, if this becomes higher priority, these two fellows will be counted in the substituent. What is the substituent name for thioalcohol? Mercapto. Mercapto. If you don't know, write it down. So you start numbering, giving higher priority to alcohol. 1, 2, 3. So at 2 and 3 we have mercaptos connected. So 2, 3 dimercapto propane 1 all, or 1 propanol. Done. That is what is your British anti-lewisite, which when reacts with this fellow will break this double bond, causing a 1, 2, 3, 4, 5, a 5-membered cyclic non-toxic compound to form. Nice and easy. Understood? Okay, fine. So I think we will let's do this last one, then we are done with the nucleophilic addition part. Yes, oxidation reaction we will start in the next class. Carbonylation, as the name suggests, what is going to get added here? Carbonyl group, C double bond O. Nice. Yes, but for that we are also using as a not exactly catalyst, as a reagent, nickel carbolate. I think NiCO4 exactly name I'm not remembering, but know this, that all these COs are connected to nickel only. Yes, correct. And when they participate, when this fellow participates, basically what happens is this leads to similar type of formation as we have seen above. If you use it with water, it will lead to the formation of acid. If you use it with alcohol, it will lead to the formation of ester. Because in case of water, who will join? Who will join? OH. It's like this. Here there is C double bond O, and here there is OH. And this gets connected to this fellow. What is this together? Acid. Nice. Here what do you have? C double bond O getting connected to the alkyne. And what do we have here? OR, H plus leaves. What is this? Ester. Correct? Moreover, triple bond breaks, double bond will form. So what is this fellow? Olefin. Double bond means alkenes. What's a common name for alkenes? Olefins. So olefinic acid, olefinic ester. Easy peasy. Can you connect? Yes. Can you connect with it easily? This is how formation will happen. So who is the olefin if triple bond breaks here? Obviously, vinyl. Yes, vinyl connected to carboxylic acid. Yes, vinylic carboxylic acid is there, which in short is called as acrylic acid. Nice. But if ester is going to form of this fellow only, you will call it as acrylate. Like how we call in ester, ethanoic acid, ethanoate. Make sense? So acrylate formation is happening here. Is this clear? CWR in place of CWH. Nice. Mechanism exactly same. But short form you have to understand. Is this clear? Fine. I think for today we will end here. Let me quickly take 2 minutes and summarize what exactly we have done. I will make it a 2-page view so that it's easy for you. I know it is too small, but we saw the introduction in the beginning. Yes. Let me slightly zoom it. We saw the introduction in the beginning. Yes, some of the physical nature, the IUPAC name, isomerism. Then we jumped down to their general methods of preparation, where the actual part started. One important part we learned was that no cis-trans isomerism takes place at the triple bond. That is one thing, keep in mind. Then we already had seen in the last chapter how geminal dihalides can lead to the formation, or vicinal dihalides can lead to the formation of alkynes. That is one thing which we saw here, correct? Then all this was like a elimination reaction happening. Yes or no? All these were like beta elimination reaction happening. All that we saw. Fine. Then we saw coal-based electrolysis. Fine. Then we saw Grignard reagent also leading to the formation of alkynes. Then we saw few laboratory and industrial methods for preparation of only ethine acetylene. Yes, which was metal carbide or calcium carbide or electric arc using high temperature Berthelot's process and all that. Correct. Then we also went for now elimination is done. Now we are seeing addition of hydrogen happening to the alkenes, correct, to ethine and all that. Now whenever addition of hydrogen has to happen, that means hydrogenation has to happen. Catalyst we know already. Yes, nickel or platinum or palladium. If it is nickel, it will be at higher temperature, 300 degree or something. If it is platinum, it will be lower temperature, correct? After that, we also saw how these alkynes can also lead to formation of either cis alkene or trans alkene based on what is the catalyst. Lindlar's catalyst or nickel boride, cis alkene, and sodium with liquid ammonia, trans alkene. We had seen it in the different chapter. Also, I should mark it here. It's very important, guys. Last chapter also we have seen. Good. Then next is the addition of halogens. We saw halogenation, correct? There dihalogenation, tetrahalogenation, all that we saw along with its mechanism. Good, fine. Yes, acetylene tetrachloride is called Vestron, how it forms Vestrosol, or tricline, which is used in the textile industries as solvents, all that we saw. So how if you add bromine water, what will happen if you add bromine liquid? It will lead to tetrabromo formation because more bromine. Yes or no? Because of more bromine. Yes. And then we saw iodine being added. If it is iodine with ethanol or iodine with ammonia, what will happen? In one case you have electrophile ready, in one case you have nucleophile ready. So accordingly, the products are different. If it is nucleophile, if it is electrophile, addition will happen. If it is nucleophile, substitution will happen. That we saw, correct? Then addition of, I hope you guys also keep flipping your pages. Go with your pages, good? So then we saw also halogen acids being added. Yes, correct? Hydrohalogenation, what we call it, following the same procedure. Then hypohalous acids, how are they getting added? Again, same mechanism, same process. Then at the end, same reaction, hydroboration, BH3 with THF or B2H6, correct? That we saw. After that, we also saw with this, the electrophilic addition is done. We jumped down to the nucleophilic addition part. For that, we learned how in C triple bond C, some heavy metal cation has to be used so that the electron density of the C triple bond C can be reduced, and hence later on a nucleophile can attack there to join with those carbons. Otherwise, till the time there is heavy electron density because of 4 extra pi electrons, nucleophile is never going to get added, nucleophile. Yeah. So for that, heavy metal cations are used. We saw hydration happening, addition of water. We saw cyanide being added. We saw acetic acid being added. We also saw alcohol in place of water being added, correct? And finally, carbonyl group being added. That's all. All good? Everybody understood? I hope. Fine.